Hello and welcome to Team 12, the Small Aperture Daylight Star Tracker, sponsored by Ball Aerospace. The prevalence of GPS use in the defense and civilian sectors has made it the target of disruption efforts, like in 2017, the Federal Aviation Administration reported 96 commercial airliners had experienced GPS interference within a 6-month period. Even more concerning, in 2011, Iranian engineers successfully spoofed the GPS of a US drone and made it land for them. GPS jamming has now motivated alternative means of global position determination, namely celestial navigation. Given an image of stars, a star detection algorithm can recognize patterns and determine the pointing direction with respect to a celestial reference frame. The direction can be used for global positioning, and this alternative system must be able to operate during the day or nighttime and produce images suitable for a star recognition algorithm. However, the principal issue our system must address is the problem of daytime star imaging.
During daytime imaging, stars are masked by a bright sky, resulting in the starlight being overwhelmed by noise. This necessitates taking multiple images and stacking them. Image averaging is frequently employed in astrophotography to limit noise and detect faint stars. Software digitally lays images on top of each other and then averages each pixel. Compare the 5 frames in the top left to the 40 frames in the bottom right and see the limited noise and the extra stars seen. Of course, this only works if the stars in the images don't move from picture to picture. To ensure that the stars are aligned in every image, we need to use gyroscopes to detect movement and account for any angular changes. This greatly reduces the noise, making the star images more apparent to the image processing algorithm. In order to counteract the problems created by daytime star imaging, one part of the solution we developed was a radiometric model. We developed a script in MATLAB that allowed us to determine the performance of the optical system and make decisions when evaluating equipment and designing the system. The radiometric model allowed us to control inputs consisting of telescope and detector parameters like focal length, aperture diameter, and exposure time. This was used to calculate the field of view of the system, which is an important consideration as it determines the number of stars the system can view at once and describes how susceptible the system is to unintended motion. Next, the script modeled stars as black-body emitters, taking their magnitude into account in order to replicate the spectrum of the stars. Using this as well as the spectrum of the sky, we're able to determine that the best wavelength range that the system should operate in is the visible range. All of this information was put together to calculate the signal-to-noise ratio, or SNR, which is a measure of the optical system performance. Since the SNRs of stars in the single image are quite low, image stacking is used to bring it up to a suitable value. We need predicted SNR values of at least 10 during the daytime for a successful star recognition.
Key system requirements address these challenges. The system shall capture images of the sky and use gyroscope data to stack those images for higher visibility. The system shall use a star detection algorithm to identify star patterns and return the pointing direction to the user. And the system's stacked daytime image shall have a signal-to-noise ratio greater than 10.
Fortunately, last year's Ball Aerospace team had some equipment for us to use. This equipment included a Newtonian telescope, a detector, and a computer. Unfortunately, is that Newtonian telescopes are actually not great for astrophotography. This is because the focal plane of the telescope and the focal plane of the detector do not quite match. In order to combat this, we decided to go with a Schmidt-Cassegrain telescope with a hyperstar lens. The hyperstar lens is unique because it changes that focal point to be from the back of the telescope to the front of the telescope, which is decreasing the focal length and increasing the field of view, or the amount of stars that we can see per image.
The optical tube assembly is mounted to a motorized gimbal, seen here. Here we have our gyroscopes, which must be mounted perpendicular to each other, which is one of the reasons the mount is so imperative. Here, this gyroscope measures changes in elevation. This gyroscope measures changes in azimuth. We use these gyroscopes to detect motion in the field of view. The telescope was retrofitted with this Vixen style rail, and this gyro mount is secured with thumb screws. Over here on this side, we have a conversion kit, which allows the secondary mirror of the telescope to be removable. The hyperstar replaces the secondary mirror, and the detector mounts directly to the hyperstar. Here, they feed into the computer. Finally, we have this counterweight to balance any torque or moment caused by this assembly up here. Before assembly, individual subsystems such as gyroscopes, image capture, and software were tested to verify that they function properly. The system was assembled and tested at night first to ensure that images could be captured, sent through the star identification algorithm, and return a pointing direction. Daytime testing occurred during the dawn and dusk hours to be consistent with the radiometric model.
With regards to our gyroscope power supply, we've exchanged our original open frame design for a lab supply owned to us by the optical department. This change was implemented due to low current outputs being produced by the first supply. Using the lab supply, the 5-volt must operate at 0.48 amps in order to receive valid gyroscopic data. To operate, activate the supply a few minutes prior to image capture to allow the gyros to warm up, and confirm the voltage and current values are at their operating levels. The gyro channels need to be switched as well, the channel 1 connection to channel 2 port and vice versa. With the gyros effectively on now, the messages are extracted and formulated to calculate the deviations during image processing.
This flowchart outlines the software process. A user can control the line of sight and begin image capture. Timestamped images and gyroscope data are read in at the same time, and both are used to properly average the image. The final image is input into the star detection algorithm to determine the pointing direction, and both the final image and celestial coordinates are displayed to the user. Gyroscopes capture angular rate data, which is read in on 2 channels. These channels detect azimuth and elevation changes. The rate data is then integrated. The resulting data streams of the 2 changing angles can be matched with the timestamped images. Thus, between any 2 image timestamps, the change in angle is known. The change in angle is related to delta x and delta y pixel shifts. Each image is shifted to keep the subject, that is, the stars, aligned during each extra image stacked. Key software interfaces allow for user mount control and image capture. The star detection algorithm we employ comes from astrometry.net. We call the star detection algorithm on the final processed images to output the pointing direction to the user.
Gyroscope connectivity issues hindered consistent testing. Spikes in angular rate data rendered many trials useless. In addition, low current values led to poor data being read slower than the expected sample rate. Still, for valid data sets, the team was able to align images using gyroscope data. One set of images were captured on a particularly cloudy night. Despite visible stars, the noise from the clouds caused the star detection to fail for a single image. But when 50 images were aligned and stacked using gyroscope data, the algorithm was successful and 166 stars were identified. This significant improvement shows the utility of image stacking using gyroscope data. By tracking the magnitude 2 star COCHAP overnight, we were able to take daytime images at dawn. Due to the gyroscopes not functioning properly, the built-in telescope tracker remained on during imaging. These images were stacked and processed, and the star detection algorithm successfully identified COCHAP and resulted in an SNR of 89. This SNR value of 89 was higher than the required 10, but lower than the predicted 126 from the model. Additionally, the pointing direction was successfully determined from this image. Furthermore, from these results, we were able to conclude that the system is able to capture and process images during the daytime, resulting in a higher SNR, and determine the pointing direction. Although these are successes, the overall system was not able to fully function as a daylight star tracker. This project's successes were due to the combination of a modeled optical system and image processing using gyroscope data. The next steps from the system will be to use the found pointing direction of the stars and determine the system's location to fully function as a GPS alternative. Thank you for listening to our project, and we would like to give a special thanks to Ball Aerospace for their continued guidance and support.